again. All right, so this is where we had stopped last time, right? How to write a Lewis-Story structure. We worked through water, molecule, and then we drew a Lewis-Story structure of a carbon dioxide molecule as well. All right, now something that you had noticed was all the atoms that we talked about either followed the duet rule, right, like hydrogen, or all of them, they followed the octet rule. That means they liked being surrounded by 8 valence electrons, right? So just giving you a heads up, my apartment complex looks like they will be mowing around my complex pretty soon. So I don't know how to deal with that situation yet, but I'll figure something out. I might just stop the class for like 4 or 5 minutes if the background noise is too loud, which I think is gonna start happening really soon. And then I'm just gonna write something in the chat box, and then I'll say something like I'll be back in 5 minutes or so, as soon as the lawnmower sound dies. All right, so we drew the Lewis-Story structures for water molecule and carbon dioxide in the last class. And we saw that all the atoms in those molecules either followed the duet rule or the octet rule, right? Now the question is, do all the atoms follow the duet and the octet rule? All right, and this is where I'm going to talk about the exceptions. I hear the background. All right. All right, so let's start with the exception to the octet rule. Can a couple of students all right, so what are some of the exceptions to the octet rule? So there are going to be lots of molecules which you're going to figure out whenever you do your VSPR lab that is due this Friday. All right, you're going to notice that yes, there are going to be molecules that are going to violate the octet rule, and that's why we're going to work on or look at them today. All right, so the two types that violate the octet rule, they're either called electron deficient molecules, and like the phrase suggests, an electron deficient molecules has less than 8 valence electrons surrounding it whenever you draw a Lewis-Story structure. All right, or the other kind is hypervalent molecule, which means the molecules has more than 8 valence electrons surrounding it. All right, so let's start with the electron deficient molecules. This, I have this periodic table because I might have to go back to show you what group I'm talking about. All right, so whenever these electron deficient molecules, whenever they violate the octet rule, they are only surrounded by either 4 or 6 electrons. All right, and then the elements in group 2 or 13. So going back to my periodic table again, right? So this is my group 2, beryllium, magnesium, calcium, strontium, barium, and radium. And group 13, boron, aluminum, and so on, right? These are the atoms that violate the octet rule. Now, you might question, all right, but then aren't the group 2 atoms or elements supposed to be metal? And that's why I'm mostly going to focus on beryllium and boron, and sometimes aluminum, but the examples that I have given are only based on beryllium and boron, all right? And these are the ones that have the covalent bonding. And that's why the example that I have here is only based on beryllium and boron, all right? And these are some examples of the molecules that they make with other atoms like BF2, BH2, BH3, and BF3, and they violate the octet rule. So let's look at some of the examples, all right? I'm gonna draw the Lewis-Joy structures of some of these, all right? And then you're gonna see how they violate the octet rule. All right, so let's say if you think about BeF2, let's start with something easy, BH3, right? So again, I'm just gonna follow the rules for Lewis-Joy structure. So I'm trying to draw BH3, right? And I know that boron is in group 3A, that's why it has 3 valence electrons. Only one atom, that's why 3 valence electrons in total. Hydrogen is in group 1A, 1 valence electrons, but there are 3 atoms of hydrogen, that's why I have 6 valence electrons in total, right? And then like I told, like the rules said that hydrogen will always be, it'll always be flanking other atoms. It is always terminal atom, right? So I draw my central atom, which is going to be boron, and I draw my skeletal structure. Right, by showing the bonding pair. All right, now the question is, I had 6 valence electrons. How many did I use? 1, 2, 3, 4, and 5, 6. And look at that. That means I'm done. Right, I'm done with my valence electrons. I can't do anything about it. All right, now let's count the number of valence electrons that is surrounding boron. Right, if you count the number of valence electrons that is surrounding boron, you're gonna see boron has only 6 valence electrons around it. All right, and that you see that, oh, but then boron trihydride, which is this molecule, right, it does not have any charge. It is neutral molecule. All right, and this is how it violates the octet rule. That's why it is an example of electron deficient molecule. All right, all right, now the other example really quick, I'm going to show you is with beryllium. All right, so let's say if you draw beryllium fluoride, difluoride, beryllium fluoride, probably correct name. So it's BeF2, right? Beryllium is in group 2, 2 valence electrons, and you have 1 atom of beryllium, that's why 2 valence electrons. Fluorine is in group 17 or group 7A, that tells you you have 7 valence electrons in fluorine atom, and you have 2 atoms of fluorine in BF2, that's why you have a total of 14 valence electrons. You add these up, you have 16 valence electrons in total. All right, now I'm going to draw the Lewis-Joy structure, and it's going to look something like this. All right. All right. Now the question that you might be thinking, right, is basically I drew the Lewis skeletal structure, right, and then what I did was I dumped all my remaining valence electrons on fluorine, so that fluorine would have or follow the octet rule, right? Now you might be wondering, okay, if you look at beryllium, if you count the number of electrons, it has only 4. Couldn't I have done something like this or not? Right, beryllium, right? Because if I do that, similar to what we did with carbon dioxide last time. All right. Beryllium looks happy, right? Now it has 8 valence electrons surrounding it in this structure, right? So then we draw this Lewis-Torch structure, right? And that's where this concept of formal charge is going to come into play. And I'm going to talk about in the next 2 or 3 slides, all right? This is not the correct Lewis-Torch structure of beryllium fluoride. This right here is the correct Lewis-Torch structure of beryllium fluoride, all right? Which shows that beryllium has 1, 2, 3, 4 valence electrons surrounding it, and it is an example of an electron deficient molecule. All right, and again, we will look through this example again whenever I talk about formal charge, and we'll decide as to why this structure is more valid Lewis-Torch structure than this structure. All right. All right, so now the other type that we're going to talk about is something called hypervalent molecules. Anytime you look at hypervalent molecule, you're going to notice that they have more than 8 electrons, right? The atom can accommodate more than 8 electrons, 8 valence electrons around it, all right? And then it can accommodate up to 10 or 12 electrons around an atom, right? And the reason for it is because these atoms, they have empty d orbitals. So think about whenever we drew the electronic configuration, right? We had s orbital, p orbital, d orbitals, right? And these atoms have empty p orbitals, and that's why they can accommodate the 10 or 12 electrons and violate the octet rule. All right. Now, so think about this. Since remember, this exam 4 is also going to be an open book. You don't have to memorize, oh, where do these atoms that violate the octet rule and can form the hypervalent molecule reside in? Right here. This is the group of atoms, right, that mostly violate the octet rule, right? So they're in group 15, 16, 17, and 18. And something that you should have noticed, very, very weird, right? Because we said that, oh, group 18 atoms, they do not like to form any bond with any other atoms. But then now you see that in period 4, group 18 with krypton and xenon, yes, they can form molecules. All right, they can form covalent molecules with other atoms. All right, but then this is the list of atoms that are capable of forming hypervalent molecules. All right, so example, let's look at some of these examples. All right, so before that, I think it's been a while. I have said any jokes. All right, put some smile on your face. I think now it might be the time to put some smile on your face. So the question is, what did elements in group 7A say to Jennifer? Group 7A say to Jennifer. Any answers? You can unmute and tell me the answer if you know the answer. You can shout it out. Remember how we classified group 1A as alkali metal, group 2A as alkaline earth metals? What did we classify group 7A as? And that's why group 7A element said to Jennifer. Hello, Jen. It's weird not to see your reaction whenever I'm doing these online jokes. All right, so moving on from halogen. All right, so examples of hypervalent molecules, right? So SF6, sulfur hexafluoride. On the left, that is the structure of sulfur hexafluoride. On the right, phosphorus pentachloride is the Lewis-Torch structure of that molecule. All right. Now, if you count the number of electrons on each of those fluorine atom, you're going to see that fluorine does follow the octet rule. Each fluorine atom is being surrounded by 8 valence electrons. Same thing with chlorine on the right. Each chlorine atom is being surrounded by 8 valence electrons. But let's count the number of electrons around sulfur and phosphorus, right? So if you count that, what you're going to notice is sulfur has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 valence electrons surrounding it, which says that this is an example of a hypervalent molecule, right? If you look at phosphorus, same thing, right? Each bonding pair counts for 2 valence electrons. I have 5 bonding pairs. That's why the phosphorus atom in phosphorus pentachloride has 10 valence electrons. All right. And when you work through your VSEPR lab, you're going to notice that, yes, most of these molecules do violate the octet rule. All right, now the moment you have been waiting for, right, as to why BeF2 was drawn the way it was, or carbon dioxide that we drew in yesterday's class, as to why it was drawn in a particular way and not the other way, even though all the atoms fulfilled the octet rule. Right, so this concept of Lewis thermal charge. So first thing to understand, right, after you draw a Lewis dot structure, every atoms in that Lewis dot structure can be assigned a thermal charge. All right, so think about this as the concept of oxidation number, right? Like how we assigned charges. This is the same thing we're doing whenever we're assigning thermal charge. The concept is different. All I'm saying is like we're tracking the ownership of electrons when we're finding the thermal charge on each atom. All right, now the formula for thermal charge for each atom. Thermal charge equals to number of, and I'm going to show you how to use this formula, right? Number of valence electrons, V stands for valence electrons, minus number of lone pair electrons, right? And again, whenever I say minus number of lone pair electrons, you are counting all the electrons, not the number of pairs of lone pair, number of lone pairs. All right, so be careful whenever I say number of lone pair versus number of lone pair electrons. All right, so think about this, right? Whenever I say I have 2 pair of shoes, all right, but then if I ask you to count how many total shoes do I have, you're going to tell me I have 2 pairs of shoes, but then I have 1, 2, 3, 4 pieces of shoes. All right, so that's what I mean by counting in pair versus just counting the total number of lone pair electrons, minus half the number of bonding electrons. And I'll show you example as to how to use this formula really soon. And a couple of rules about thermal charge. Yes, like I said, this formula can be used to check your Lewis dot structure, and that's one of the reasons I'm teaching you, right? And then, all right, so let's start with the thermal charge on atoms in a laughing gas. All right. So laughing gas, yes, like the name suggests, it does. If you inhale it, you will laugh your butt off. Excuse my French. All right, and it has a molecular formula of N2O. All right, so we're gonna draw 2 Lewis dot structures of N2O, and then assign the thermal charge on each of those atoms. All right. All right. So first, let's focus on using the formula of thermal charge. Yeah. All right. So whenever you draw the structure of N2O, all right. So I'm going to save some time, and then if you want to practice drawing the Lewis dot structure of N2O, make sure you do that. All right. So N2O is going to look like this. I'm going to draw it big. N. O. All right. So let's learn first before I show you the other structure of N2O, and before we predict which one is the better structure, let's learn how to assign the Lewis structure, sorry, the thermal charge on this molecule. All right. So for this, I'm going to start using my formula, right? My formal charge formula tells me. So I'm going to start looking at this nitrogen on the left first. So my formal charge on that nitrogen, right? Nitrogen formal charge equals to, my formula tells me number of valence electrons. So nitrogen is in group 5A. That tells me this nitrogen has 5 valence electrons. All right. Minus the number of lone pair of electrons. Again, I am not counting it as a pair. I'm counting individual lone pair electrons, right? So 1, 2, 3, 4. Minus half of bonding electrons, right? So I have 1, 2, 3, 4 bonding electrons. I hope this makes sense, right? So if I do the math, this nitrogen is going to have 5 minus 4 minus 2 equals to 5 minus 4 is 1 minus 2 is negative 1 as its formal charge. All right. So I would you take your time and see if you can figure out. I'm going to give you like 30 seconds if you can figure out the formal charge on this nitrogen atom and then this oxygen atom. Go for it. 30 seconds by using that formula, and make sure you're able to use that formula because you'll definitely have this question on exam 4. All right, so let's do the nitrogen in the middle. Nitrogen in the middle, formal charge, formula equals number of valence electrons, same thing, it has 5 valence electrons. All right, minus lone pairs, it does not have any lone pair, right? 0 minus half the number of bonding electrons. It has 1, 2, 3, 4, 5, 6, 7, 8 bonding electrons. That's why if I do the math, I'm going to end up with +1. All right. If I do the same formula for oxygen, this oxygen is going to be oxygen equals to number of valence electrons. It has 6 of them minus. All right. Number of lone pair of electrons. It has 1, 2, 3, 4 lone pair electrons minus half the bonding electrons. Half times it has 1, 2, 3, 4 bonding electrons. If I do the math, I'm going to end up with 6 minus 4 is 2. 2 minus 2 equals to 0. All right, so I hope this formula, how to use it, makes sense. So something that you should have noticed, right? So I'm going to go and clear this canvas, and then I'm going to write the formal charge on each atom based on this calculation that I did. All right, so my N2O, this N2O structure, right? With my calculation, I found that this nitrogen has -1 charge, this nitrogen has +1 charge, and this oxygen has 0 formal charge. All right. Now, let's look at another possible Lewis structure of N2O, the laughing gas. All right. So the other possible structure for N2O is this. right? Now, whenever you draw this Lewis structure, what you're going to see is both of this structure, all right? They are following the octet rule. All the atoms, they have 8 valence electrons surrounding it, all right? Now the question is, which Lewis structure is better? Or how can we use the formal charge to predict the better Lewis charge structure? Now, whenever you calculate the formal charge on this Lewis charge structure, what you're going to notice is the formal charge is going to look something like this. This nitrogen is going to have 0. This nitrogen is going to have +1. And this oxygen is going to have -1. All right. A couple of things that you should have noticed, right? Laughing gas N2O, it is a neutral molecule. It is not a polyatomic ion. It is a neutral molecule. Overall, it's neutral, right? And if you look at, after I calculate the overall charge, look at this. If I add up the overall charge, -1, +1, and 0, look at that. Overall formal charge is 0 for N2O. Same thing for the structure in the bottom, right? +0, +1, -1, it adds up to be 0. All right. Now the question is, which is the better Lewis choice structure? Let's look at the rules now and see if we can figure out. All right. So I'm stopping right now because there's lawnmower right beside my house. I'm going to stop for like 2-3. I'm going to stop talking for 2-3 minutes. Okay, I think he did his stuff. Sucks. All right, so the most likely Lewis structure will have formal charges as close to 0 as possible. All right, it's gone far away. All right, so meaning that, let's say if you calculate the formal charge on each atom, right? You do not want the atoms to have, let's say, +3, +2 formal charge. If it's close to 0, such as -1, +1, it will be better. All right, so that will be most likely the correct Lewis choice structure. The next one, adjacent formal charge of 0 of the opposite sign, right? So that means if you have -1 and -1 in the atoms right next to it, that is not a valid Lewis structure, right? You want to have, let's say, +1 and -1, even if you have any charges adjacent to each other. Now the last one, which we're gonna use to figure out which is the valid or most likely Lewis structure for the laughing gas, is it says if there must be an atom with a negative formal charge, which we saw in our case, right? In one of the structure, nitrogen has the -1, whereas in the other structure, oxygen had the -1 formal charge, right? It says that then it is assigned to the most electronegative atom in the structure. All right, let's look at our structures now, right? So if you look at the one on the top, this is one at the bottom, right? The one on the top, yes, look at that, those, right? First thing is the charge is like -1 and +1 and 0, they are pretty close to 0. And the negative and the positive charge, -1 and +1 charge, are adjacent to each other. All right, but then that's the case for the both the top and the bottom Lewis choice structure. Now the last one, it said that if there must be an atom with a negative formal charge, then it is assigned to the most electronegative atom in the structure. All right, now this structure has -1 on oxygen atom, whereas this structure has -1 on the nitrogen atom. That's the only difference, right? My rule says that the -1 formal charge is better on the atom with higher electronegative number, or the atom which is the most electronegative, since oxygen is more electronegative than nitrogen. And again, think about that trend in the periodic table, right? We said that the electronegativity increases as you go across a period. All right, since across the period you're gonna have something boron, carbon, nitrogen, oxygen, right? So this is what your periodic table is going to look like, and tells me that oxygen has higher electronegative number than nitrogen. That's why we want the -1 charge, formal charge, to be an oxygen. And that's why this is mostly the correct or most likely Lewis structure of laughing gas. And this is how we can predict the Lewis structure of laughing gas. All right, and I'm gonna assign something for your homework now. All right, just for you to practice. In my earlier, when we talked about electron deficient molecule, right? I'm gonna erase this now. Right, we drew BF2 as this, right? And I posed you a question as to why I couldn't have drawn something like this, because the second structure makes sure that beryllium fulfills the octet rule. All right, so for your homework, what I want you to do is I want you to assign the formal charge on each of these atoms here. Do the same thing for each of these atoms, and then see if you can use the 3 rules that we just talked about, the most likely Lewis structure, and figure out why this is the most likely Lewis structure and not this one. All right, so again, this is for your homework. Make sure you work through it. This will give you a practice on how to use that formal charge formula and to how to figure out which is the most likely Lewis structure based on the formal charge. All right, so now we're going to talk about something called Vesper theory, right? And then why some molecules have the shape that they have. And then definitely we're going to talk about this concept of polarity. What does a polar molecule mean? What does a non-polar molecule and such? All right. So if you think about diatomic molecule, all right, I'm going to hold on. I think the lawnmower is pretty close, right by my apartment. So let's wait for about 2 to 3 minutes. And this might be the time if you want to just look at those BEF2 structures and see if you can assign the formal charge based on the formal charge formula. See if you can figure that out while I wait for the lawnmower to quieten. If you have any questions right now, you can just send me in the chat box. Again, I'm just waiting for this lawnmower to kind of so that you can hear my voice. So make sure you're working on the BF2 formula. And this fluorine, I think it's all right. And this is going to be a good practice for you for an exam 4. Something that I want to tell you is I am not going to give you a molecule that you can literally Google and draw the Lewis charge structure of and calculate the formal charge. All right, which probably if you just Google it, you're going to find the answer. I'm just going to give you some imaginary molecule. All right. and then I'm going to ask you to calculate the formal charge. So do not expect that, oh, if I Google the structure for exam 4, I'll be able to find the formal charge and I'll be able to just not or find the easy way out. For example, I am going to give you some imaginary molecules, a lot of them actually. So make sure you're comfortable using this formula. I'm going to move on now. I think my all right. So again, if you just think about this linear diatomic molecule, right, like H2, HCl, Cl2, right, or even like molecules which have only 2 atoms, such as HCl, right? It is easy to visualize what they look like, right? It's literally just a linear molecule, right? It has no choice but to be in a linear fashion. But then if you think about the atoms that have, or molecules which have more than two atoms, right? So that means 3 or more, their molecular shape, it is not always obvious. And that's what we're going to focus on as to how can we, is there some kind of a table or trend to figure out the molecular geometry of some of these molecules, right? So I'm going to show you what I mean really quick. I have this molecular model kit here, all right? So if you look at this right here, right? So this is an example of, let's say, Cl2 molecule, all right? It's completely linear. It doesn't matter if I rotate it this way or this way or this way, right? It's completely linear, right? You can think about this as one oxygen, this as on the oxygen and being bonded, and this is a bonding pair. I hope you all can see this, all right? Now let's make it a little bit harder. How about methane? So methane has a chemical formula CH4, right? Carbon bonded with 4 hydrogens. So if you draw the Lewis-Strauss structure, you're gonna draw everything flat, right? Because your paper is flat. CH4 is flat, all right? But the current structure was this, looks like this. So this central atom right here, the black atom, that's my carbon, all right? And these red atoms that surround it are my hydrogens. So do you see how this structure is not flat, right? Like the way you would draw in paper, it is not flat. In fact, we have a particular name for this. We call this a tetrahedral geometry or tetrahedral molecular shape of methane. And we're going to learn to figure out, oh, how do we know which molecule will have what molecular shape in the next 2 or 3 slides. All right, so I'm going to rotate it. So do you see how this has like weird 3D shape? I want to say weird, but tetrahedral shape. So that's what I'm talking about when I say molecular shape. All right, so now the question is, how do we figure out this 3D shape and the name for these molecules? All right. So before that, really quick, I do want to make sure that you understand this concept of bond angle, what it means. All right. So if you look at the definition of bond angles, it says the angle between any 2 bonds that include a common atom. All right. So if you look at COH2 molecule, right, that you see right here. So this is what its Lewis structure looks like, right? So whenever I'm talking about bond angle, what I'm talking about is the angle between any 2 bonds, right? So this bond angle that you see at 118 degree, that include a common atom. That means these 2 bonds include this common atom carbon. That's why you can talk about the bond angle here. Same thing over here, all right? The bond angle between HCO, you can definitely calculate the bond angle, not calculate, I would say know the bond angle or how to figure it out. But then this is what I'm talking about whenever I'm talking about the bond angle of HCNO, all right? Because carbon is the common atom between this bonding pair and these bonding pairs. All right. All right. Now, to figure out the molecular shape, we talk about something called VSEPR. whenever you use the term or phrase VSEPR, it means it stands for valence shell electron pair repulsion theory. All right. And what it means is easy way to think about this, right? I want you to look at this balloon model.
We can't see your screen.
Hey, all right. Thank you. Thank you. Yes, and you can shout it out. If I forget to share screen or share audio, do shout it out. Or you can even say hello, Zen, and I'll remember to turn my screen on. All right, so VSEPR, VSEPR stands for valence shell electron pair repulsion theory, right? So to think about this more, right, let's just look at the easy example. So if you look at the balloon model that you see here, whenever I tie the two balloons together very tight, right? Versus 3 balloon together, versus 4 balloon together, versus 5 balloon together, versus 6 balloons together, right? Trust me, no matter how hard you try, this is the structure, if you want to call it, or the shape that you're gonna get, where the balloons are gonna stay as far apart as possible. All right, and that's what valence shell or the valence shell electron repulsion VSEPR model or theory tells you. All right, the concept is, first thing to keep in mind, right, this molecular geometry that we talk about, or the balloon that we're separated out, is based on the electron pair repulsion, right? Because remember, it takes 2 electrons to make a bond, and whenever you form a molecule, there are lots of bonds that are forming, right? So the molecular geometry is based on all those electron pair repulsion, the electron repulsion between the bonding pairs, the electron pair repulsion between the lone pair electrons, and such. All right. So whenever those repulsion happens, right? So something to keep in mind, right? Those molecules, those atoms are trying to form a bond, and at the same time, they're trying to be as far as possible. All right. And VSEPR model, basically, all it tells you is that all these repelling of these bonding pairs and lone pairs and the orbitals that form become oriented there, so they're as far apart from each other as possible, like the balloon model I showed you. All right, so each example is, think about carbon dioxide, it's going to be linear as shown on the left, right? Carbon dioxide is here. If you think about sulfur trioxide, it's going to look like this orange ball with 3 red, but then it's going to be a planar structure, completely flat, like this balloon here. But if you look at our methane CH4, right, the model that I showed you through a video earlier, it's going to look like this, and so on. All right. Now, the good thing about exam 4 is, since it's open book and open note, unlike distance from previous semesters, you do not have to memorize all these as to, oh, whenever you have iodine followed by or surrounded by 5 fluorine atoms, going to have trigonal bipyramidal. But the question is, how do you know which molecular shape it takes, whether it takes linear or it takes tetrahedral? That's where I'm going to show you a table that you should have memorized if you're still last semester, but this semester it's open book and open note. Just understand how to use that table is what I would suggest. All right. So first thing, before you understand those table, let's think about if you have a central atom. Let's call that central atom A, right? So it can be surrounded by a certain number of electron pairs, or even atoms, other atoms. All right. So what I mean by that is something called the AX notation. So let's think about my central atom as A, all right, which can be surrounded by some number of atoms X. So again, whenever I'm talking about X, I'm talking about, think about those more like the terminal atoms, all right. And then E stands for the lone pair, number of lone pairs. You are not counting the individual electrons. You are counting the number of lone pair. All right. So whenever you have these kind of cases, right, we have something called this table. Right. So if you look at this table, you have AX2, AX3, AX2E, AX4, AX3, right, on the first, second, third column. So what I mean by that is these molecules have a central atom, one central atom. The X2 stands for it has two terminal atoms. All right, let's go to AX3. Whenever you look at AX3, it's telling you have a central atom A, and then you have three terminal atoms X. But whenever you talk about AX2E, what you are telling me is it has a central atom A and then two terminal atoms, and that A, that central atom A, has one lone pair of electrons. Right. Again, I will show you some examples. Right. I just want to make sure you understand how to read this abstract notation. All right. So now I'm going to talk about steric number, and I'm going to use the lingo that your Vesper lab uses. So make sure you listen to me carefully. All right. So whenever we talk about steric number, what I'm saying is you are counting the number of electron group around it. All right. I think Vesper lab uses this term called electron group. All right. So let's see if you have AX2, right? It says linear. So A instead of E2, you have X and X. But do you see how this bonded pair is going to be counted as one steric number? This another bonding pair is going to be counted as two steric number. Or again, steric number is the same as electron groups. All right. And again, I'll show you some real examples, and hopefully this will be more clear. I just want to make sure you understand what this steric number means. All right. So again, remember, this will be given to you. It's open book and open note. All right. So let's look at how to use this example. All right. So to use this example, so let's say if I drew the structure of a molecule, which I have right here, and I said that BeF2 looks like this, right? The one on the top. Now, if I write the notation, my central atom is beryllium, so I'm going to denote that by A notation, right? And my terminal atom are two fluorines. That means I have two of those. That's why AX2. Do I have any lone pair of electrons on beryllium? No. That means I can write this as E0 because it doesn't have any lone pairs. That means if I have AX2 E0, that's the same as AX2. AX2, I can write my 2 here. All right, now I go back to my table. All right, and I find my AX2, and look at that, my AX2, it tells me that AX2 is going to have a linear molecular shape. That tells me that BeF2 has a linear shape. All right, let's try a little bit harder ones. All right, so let's try water here. All right, so if you draw the structure of water, I'm going to erase all this, clear my canvas. And again, it's 9:53 a.m. If you have other class to go, I'm going to go for under 7 or 8 minutes. All right, if you have water here, this is what we said the water structure looks like. Right, based on the loose structure you came up with, this is what it looks like. So let's learn how to write the notation in that AX2E format. All right, now remember, A refers to the central atom. I have only one of those, right? There are two terminal atoms, hydrogen and hydrogen. That's why I'm going to call it AX2. All right. Now I look at my lone pairs on the central atom. Again, I'm only looking at the atoms, atom A or the central atom, to count my lone pairs. I'm not counting the lone pair of electrons on my terminal atoms. So one lone pair, two lone pair. So I can write down something as AX2E2. Again, I'm counting the pair, lone pair, all right, not the total number of electrons in those lone pairs, all right, just count the lone pairs. That means I came up with the notation AX2E2. So I go back to my table, and if I scroll down underneath trigonal pyramidal, all right, you have something called AX2E2, which I cannot seem to. It's not letting me do. Anyways, underneath AX3E, all right, there is something called AX2E2, all right, and then the structure of that is going to be called bent, and that's why right here, do you see that AX2E2? That's why it's bent. All right, now again, like I told you, the steric number Sn, the easy way to find the steric number is, first you can just literally find your subscripts in your notation, right, and then add all of them up. For example, do not count the subscript for the central atom, but do you see how this X has two subscripts? That's why it has two steric number. Let's look at AX2E. X has two subscript, E has one subscript. If you add them, 2 plus 1, that's 3. That's how you can figure out the steric numbers, or in other words, steric number is also known as electron groups. For example, AX3, I just look at X, there is 3 of them, that's how I come up with 3. All right, now let's move on. So far we just talked about 2, 3, and 4. All right, and something that I forgot to tell you is these angles. All right, so linear, it has 108 degree. Your molecules with steric number 3 will have 120 degree angle, bond angle. Now there are some exceptions when you have lone pair, and we're going to talk about that whenever I solve some of these whisper problems on Friday, as to what happens if you have a lone pair in AX2E. Is the angle always 120 degree or not? I'm going to talk about that in class on Friday. All right, and finally, with the molecule which has steric number of 4, their bond angle is 109.5. Right, we can go on. Right, if you have 5 steric numbers, all right, look at that. This atom, if it is surrounded by 5 of the atoms or lone pairs, right, it can have shapes like trigonal bipyramidal, seesaw, T-shaped, linear, depending upon what molecular shape or notation you come up with. Same thing if you have 6 steric number. All right, different names and different notation. All right, again, this is kind of an abstract concept, but then again, as you start drawing those Lewis-Strauss structures, trust me, all this shape will come into play. As soon as you draw the Lewis-Strauss structure and then you come up with these notations, you'll be able to figure it out. All right, now I've given some examples of these molecules. So this is the same slide as the other one, but this slide has some of the examples of molecules with this particular shape. That means what I'm telling you is, if you have this AX2E0 notation, right? In my earlier slide, it told me that, oh, it was linear, and these are some examples on the right-hand column that says that BeCl2, HgCl2, CO2 are some examples of molecules that end up being linear. right? AX3 E naught, we said in our earlier table, that's trigonal planar. All right, so these are some examples of the molecules that have these molecular shapes, right? Tetrahedral, these are some of the molecules that have this shape, and so on. All right, and if you look at this structure model, right, it shows you how do they look in 3D shape. So if you want to kind of visualize octahedral, you can look at this shape, right? If you look at the geometry, right, you can look at this shape as to, oh, there is a central atom A, right? And then it's been surrounded by 6 of these atoms. All right, and that's why it has an octahedral shape. And if you want to look at the origin of some of these shapes as to why it's called an octahedron or tetrahedron, you can just Google it, and then it's going to tell you why it's called a tetrahedron, or why this shape is called an octahedral. All right, but I'm not going to go into depth into that, because you can literally just see the geometry and what would it look like in the 3D shape. I'm going to work through this question, this last question, and I'm going to call it a day. All right, the question about how does Alex asks you this question. All right, so the question asks you, and let's see how to use that table. It says, answer the question in the table below about the shape of the azide anion, N3 minus azide anion, N3 minus anion. And it asks you how many electron groups are around the central nitrogen atom. And again, electron group is the same as steric number. And that's why I used that word interchangeably earlier. All right. And then it asks you what phrase best describe the arrangement of these electron groups around the central nitrogen atom. All right. So first thing to answer this kind of question, what you have to do is you have to draw the Lewis structure. And again, I have 2 more minutes and I'll finish it. I promise. All right, so azide anion N3 minus. Right, so if I fulfill the octet rule and all those things, this is what azide anion is going to look like. Right, and you might be wondering why this is the shape, better shape than this. And again, I use the same than this, right? I could have done something like this along this line. And again, I'm telling you this is the better shape because of whenever you use the formal charge and assign the formal charge on all these atoms, this is going to be your better shape based on the 3 rules that we talked about. All right. So now after you draw the Lewis structure, I'm going to write my notation, right? The AXE notation, right? So this is my central atom, nitrogen, right? So there is only one. So I'm going to write down A for this. There are 2 terminal atoms, right? 1 terminal atom, 2 terminal atoms. AX2. All right. Is there any E here? Right, I do not see any lone pair on this nitrogen, right? No lone pair on this nitrogen, so I can write that down as AX2E naught. All right, so I came up with this notation AX2E naught based on the Lewis dot structure. So after I write my notation AX2E naught, right, what you can do is whenever the question asks you how many electron groups are around the central nitrogen atom, right? What I do is I count the subscripts in my AX2E naught. All right, and then I do not count the A, right? I just count the 2 from the X and then 0 from the E. That's how I end up with 2 electron groups. Or what you can do is if you want to go back to this table and use this, be my guest, right? So AX2E naught is the same as this. And look at the steric number is SN steric number is 2. That means I told you the steric number and the electron groups are the same. And that's why 2 is the number of electron groups around the central nitrogen atom. All right, now the final question, and I'll stop here. It says, what phrase best describes the arrangement of these electrons groups around the central atom? Right, it's the same as molecular shape. I go find my AX2E0, which is right here, right? It's take number 2, AX2E0, and look at that molecular shape. The molecular shape is going to be linear. All right, so I'm going to end here. I'm going to continue with this couple of questions from Vesper Lab. If you have done it, good for you. If you have not, this will probably give you a better idea as to how to solve some of these problems in the next class. All right, I hope you all have a good day. I'll be on for like under 2 to 3 minutes if you have any questions, and I'll hopefully see you on Friday. And yes, you do have a quiz on Friday. All right, I will send you the detail about quiz this Friday, probably by early morning tomorrow. But make sure you are working through some of these problems, some of the examples that I worked out, and make sure you are able to do it based on the examples that I worked out. Again, Lewis-Torrey structures, it does take practice. It is not, if you are looking at the Lewis-Torrey structure the first time, it is going to take time. Have patience, all right? And I will see you all on Friday. And if you have any questions, I will be here for another 2 to 3 minutes. I hope all of you have a good day. Okay, my chat box.